Hello, welcome back. So in this video, I wanted to cover a few simple DTFTs and how they manifest. So the properties of DTFT are something I want you to read on your own. I will provide you a note. You can look at them. But in this video, I want to look at some simple DTFTs. Let's start with the simple exponential sequence. And I'm also telling you that a is a real or complex number, so that mod a is less than 1. Let's plug this into the formula. Okay, summation a power n un e power minus j omega n. Now notice that because there is un inside here, I might as well just take the summation from 0 onwards. And I'll take this common. This is a geometric summation which can be summed because the magnitude of this is less than 1, and you get okay. So this is the DTFT. Okay. Still, what intuition am I supposed to get? It turns out that let's start with something very simple. If you put omega equal to 0, you get 1 upon 1 minus a. I'll just write it on the side. Omega equal to 0 is also called the DC value, and if you look at the summation, putting omega equal to 0 translates to summing the full sequence. So putting omega equal to 0 in the DTFT just gives you the sum of all the values of the sequence, which is 1 upon 1 minus a. Similarly, putting omega equal to pi will reveal that this will become 1 by 1 plus a. So what does putting omega equal to pi mean? That means that you are summing each value of the sequence but alternating the sign of successive values. How? In this case it will be a power 0 minus a power 1 plus a power 2 minus a power 3, because you are putting omega as pi, which is minus 1 power n. So it will be a power 0 minus a power 1 plus a power 2, minus a power 3, and so on. And if you sum that, you get 1 plus a. So let's say that a is actually some number like 0.9. Let us sketch this magnitude. Let's sketch the magnitude of h of e per j omega. Okay, minus pi to pi. So actually, if you plug in the value and if you evaluate the magnitude, you will find, and you will sketch it, you will find that it looks something like it's not very well drawn, so it has to be symmetric. Okay, and there's a continuity. So again, the same value will start here, and again you'll get the periodicity. Okay, and the value over here will be 10. The value over here will be 1 upon 1.9. Why? Because 1 upon 1 minus 0.9 is 10. 1 upon 1 by 0.9 is something like close to half. Now what does this mean? This means that there's a lot of low pass content, meaning there's a lot of lower frequencies present in this signal, lesser of higher frequencies. Of course, it's not very obvious what that means, but if you were to express this as the summation of discrete time sinusoids, this will have more of lower frequencies in it than higher frequencies. Okay, that is one intuition which you can take away. Okay, fine. Let's do something even simpler. Okay, let's take another sequence. Let us actually take the sequence. Let us take the sequence delta n plus delta n minus 1 plus dot 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 plus delta n minus m plus 1. Okay, that means this is basically the m length window. because it stretches from 0 to m minus 1, right? So it goes like this up to, so this is 0 to m minus 1. There are m non-zero elements. This is a finite sequence. Obviously it's absolutely summable. So you can directly just write the Dtft by plugging it into the formula. You will get 1 minus e power minus j omega m by 1 minus e power minus j omega. Here you have to be careful. You may say that if I put omega equal to 0, then this is not defined. But be careful. This is actually, when you put omega equal to 0, both the numerator and denominator become 0. So you have to not do it that way. You have to take limits. Whenever you have 0 by 0, you have to take limits, and you will find that it will actually even out. And remember that I told you what happens when omega equal to 0. When omega equal to 0, you will get the DC value. You will get 1. You can either take limits or you can simplify, and you will find that it is 1. This actually has a simpler representation. In fact, if you do this nice manipulation, look carefully, this comes in very handy. You just take e power minus j omega m by 2 out, and the numerator you get e power j omega m by 2 plus e power minus j omega m by 2, minus e power minus, let me write it clearly, minus e power minus j omega m by 2 upon e power minus j omega by 2 in the denominator, and e power j omega by 2 minus e power minus j omega by 2, and if you simplify this, this turns out to be e power minus j omega m minus 1 by 2 sine, because this you can add and divide both by 2j, sine omega m by 2 by sine omega by 2. Notice that this looks like a sink. It's not a sink because sink has sin x upon x or sin pi x upon pi x. This is not exactly a sink like a sink, but it looks like a sink. In fact, if you visualize this, and that is something which you will do as part of your homework, it will look like a a sink-like character. Now you know that a rectangle has a sink. So even in the discrete time, the rectangle has a sink-like function. Okay. Let's do a couple more. Okay. So let's look at another simple sequence. Okay. Let's take a particular version of this and we'll look at these. So for example, let's say we have delta of n plus delta of, so let's take delta of n minus delta of n minus 1. That is, this is this sequence, right? I mean, it's just this sequence 0, 1. So for this, if you find the Dtft, it will be 1 minus e power minus j omega. That is actually, again remember my trick, I took e power minus j omega by 2 out, multiplied by j2 sine omega by 2. In fact, this part is symmetric about omega and this part is e power minus j omega by 2. If you remember, delta of n minus n naught had a Dtft of e power minus j omega, right? Omega, right? E power minus j omega n naught. Okay. Let's actually take a variation of this. Let's take okay. For this you will get 1 minus e power minus j 2 omega, and this is equal to, if you do the same thing by taking e power minus j omega out, e power minus j omega into j2 okay, this is interesting. So I get an e power minus j omega out, but you know e power minus j omega corresponds to delta of n minus n naught. Okay, so if you read the properties of the Dtft, a very important property is the convolution property. So that means that this corresponds to e power minus j omega. Basically, e power minus j omega corresponds to delta of n minus 1. And what about j2 sine omega? J2 sine omega is very easy. It's actually e power minus j omega, so e power j omega rather, minus e power minus j omega. That's what it is. Now this is the convolution of, so e power j omega is delta of n plus 1 minus e power minus j omega, which is delta of n minus 1. Okay, this just says that you can obtain delta of n minus delta of n minus 2 by shifting delta of n plus 1 minus delta of n minus 1 to the right by 1. Okay, very obvious. So what about it? The interesting thing is that this Dtft can be split into two parts. The first part being something which is akin to a pure delay, and the second part being something which is the Dtft of another sequence. Okay, so now notice that there's this notion of causality. If you remember, causality means that, or to give you just the definition, a sequence is said to be causal if it is non-zero only for n greater than or equal to 0, that it's right-sided beyond 0. This is a causal sequence. Okay, because it's 0 for n less than 0. And we are basically taking this is actually a non-causal sequence. And we have shifted it to the right to make it causal. That's one other way of interpreting it. But one important thing is that there is another notion. If you notice this sequence, this is this sequence. This is anti-symmetric about the point 0. That is, to the left of 0 it's plus 1, to the right of 0 it's minus 1, but it's anti-symmetric. That is, this sequence satisfies okay. Why? Because if you put n is 0, you get x of 0 is 0, n is 1, x of 1 is minus x of minus n. So this sequence is actually called an odd sequence. Okay, and if you remember your properties, an odd sequence will have a purely imaginary Dtft, which is true because its Dtft is j2 sine omega. Omega is a number between minus pi and pi, so j2 purely imaginary. Okay, and you are making it causal. So it's interesting that you're able to split the Dtft in this case into a symmetric part and just a delay. That is something I'd like you to observe. Okay, we'll do one more example. Okay, and this example is something which is very simple. Let's do cos omega naught and sin omega naught n. Okay, now there are multiple ways of doing this, but let's do it using the property that multiplication in the time domain corresponds to convolution in the frequency domain. Okay, so I'll take sin omega n. So sin, okay, if you look at the sin, it is basically going to have if you look at the sin, it's going to have two impulses. Okay, weight half at omega naught, weight minus half at minus omega naught, and periodic with 2 pi. I am not drawing the others. And I have to convolve this. Remember, multiplication in time domain corresponds to convolution in the frequency domain. I have to convolve this with the cos, which has, okay. Now here is the interesting part. If I convolve, then I just have to take this part and then shift it to the right by omega naught, shift it to the left by omega naught. But what is the guarantee that it will not cross pi on the right and on the left and things like that. So those kinds of problems will start to occur. So for example, if you want to look at it in a simpler way, this is actually half sine 2 omega naught. So then suppose you chose omega naught to be 0.8 pi. So 2 omega naught will be 1.6 pi, and 1.6 pi is actually minus 0.4 pi, or it will wrap around and come back. So these kinds of problems will occur. So suppose that omega naught is less than pi by 2. Okay, in this case it is less than pi by 2. Then the convolution is easy. The convolution is going to give you're just going to place this at 2 omega naught. Okay, I'm going to shift this, and this goes to 0. I'm going to draw it with a dotted line, so it's minus half. And I'm going to shift it to the left, so this goes to 0. These two cancel out, and you're going to get a negative at minus 2 omega naught. There's a J over here. Okay, I forgot that. And this corresponds to a weight of, because there's a half multiplication here, there's a weight of 1/4, 1/4, and it's very obvious to see that this corresponds to half sine 2 omega naught. Okay. Of course, you should really just use this 2 sin theta is sin theta, 2 sin theta cos theta is sin 2 theta formula, but still, I'm just saying that this works out. Okay. Okay. So, try to look at the other properties of the Fourier transform, which is available in the book, and get some practice done, and you can understand. And all the other intuition is always try to have the picture clear in your mind. That will help significantly. Thank you.